Hello, everyone. This is Sujaya, and today I will be talking about our work called QuORAM, which is about building a fault-tolerant, oblivious data store. This work is done in joint collaboration with people from UC Santa Barbara, University of Washington, and at Oracle. Today, we all understand the importance of data privacy in our day-to-day interactions. When we think about data privacy, the first thing that we think of is data encryption, which is the first obvious solution. Here, I'm considering a toy example of a pharmaceutical company that produces 4 types of medicines. And this company encrypts this data and stores the encrypted data on third-party cloud providers that may not necessarily be trustworthy. Here, I'm specifically talking about honest but curious adversaries that are not going to actively manipulate the data, but will passively observe and try to learn some information about the system. Researchers have shown that just data encryption is not enough to preserve data privacy. And here is a very simple attack. I have the encrypted data stored on the external server, and I have clients buying medicines and hence interacting with this data. The adversary, over time, builds a confidence model where it learns what % of the time what row is accessed. Now, completely independent of this, another pharmaceutical company produces its yearly sales statistics and publishes this publicly. Now, the adversary, having access to its personal model and this publicly available information, can map the two and learn that next time when a client accesses row number 4, very likely the client is buying medicine for breast cancer. These kinds of attacks are called access pattern attacks. And in fact, there has been a large number of work that show that even encrypted data can reveal sensitive information through access patterns. And oblivious RAM, or ORAM, is a cryptographic technique that mitigates access pattern attacks. The core idea in ORAM data stores is to make the data accesses on the external server look completely random. And a typical ORAM data store has the following architecture. There is the external server that stores the encrypted data. There is a trusted proxy that stores the encryption key, as well as any metadata necessary for the ORAM scheme. And the adversary typically controls all of the communication channels in the system. To give an intuition on how does ORAM solutions actually hide access patterns, let me take a quick minute to explain Path ORAM, which is one of the most well-known ORAM protocols. Path ORAM structures its data on the external server in a tree-like structure. When a client wants to read or write the data, let's say this orange block of data, it sends the request to the proxy, which then translates this into a physical read where it reads the entire path of the data where this block is located. This is step number 1. In the second step, the proxy shuffles and writes the shuffled path back to the external server. And once both steps are complete, it acknowledges the client's request. So essentially, by randomly changing the location of the block after each time it is accessed, ORAM solutions are able to provide access pattern obliviousness. And the takeaway point here is that Path ORAM and most existing ORAM solutions for every single request achieve this by reading the path once and then shuffling and writing the path in the second step. So having given a high-level intuition on how ORAM solutions hide access patterns, let me now explain the issue with existing data stores, ORAM data stores, in that they're not fault tolerant. If my external server crashes, because it stores all of my data, I lose all of that data. But even if the proxy crashes, because it stores the encryption key, the application ends up losing access to the data. So if either of these entities crash, the application loses access to all of its data. I want to take a quick note to mention OBLADI, which is a recent work that provides data durability guarantees in obliviousness settings, but it doesn't give any liveness in that while the proxy is down, the application cannot access any of its data. So given this issue, in this work, we propose QuORAM, which is the first fault-tolerant and replicate a WS data store that achieves replication using a quorum-based solution. QuORAM's system and threat model are as follows. Because if either the server or the proxy crashes, I lose access to all of my data, we bucket these two entities into a single unit and replicate the data across n such units. And the clients have an all-to-all communication with the proxies in the system. Now, to tolerate F crash failures, QuORAM replicates the data across 2F+1 replicas, and it tolerates honest but curious adversaries that can control all of the storage servers as well as the communication channels in the system. Now, having described its system and threat model, let us now define the 3 goals that we want QuORAM to achieve. At its core, it is an oblivious data store, so we want it to hide access patterns. We wanted to give us fault tolerance, and for this, we wanted to replicate the data. And we want QuORAM to achieve linearizable semantics. What linearizability states is that if I consider a single data item that has multiple read and write requests on it, all these requests must appear linear to the external observer. And so in describing how QuORAM achieves these goals, for now, let me just assume that we're going to use some black box solution to hide access patterns, and let me focus on how to replicate the data and achieve linearizability. Now, we have to be careful when either picking or designing replication protocol, because it can be quite expensive to communicate with geo-distributed replicas. And so in the first naive solution, I'm going to use an existing efficient replication solution, such as Hermes or Crack, that are optimized for read operation in designing QuORAM. These operations for read request, the client reads from a single unit, and for write request, the client writes to all of the units. And we see that it is read optimized because read is accessing just one of the replicas. Now, if you look carefully here, because the adversary controls the communication channels and can observe these messages, just looking at the number of message exchanges, the adversary can understand if the client is performing a read request or a write request. And so this breaks obliviousness. What we then need is a solution that accesses the same number of units for both read and write operations. And so let this be the second solution, which is also an optimized solution because it is executed in a single round where a client reads from a majority for read requests, and when for write requests, it writes to a majority. Now, to see the issue with this protocol, let us consider an example where all 3 units store an item X whose value is 5. I have a client that is performing a read on units 1 and 2, which are a majority. And the first message goes through fine, so it updates the data. And the second message is still on its way. And due to the asynchrony in the network, there is some message delay. At this exact point, another client is now going to perform 2 consecutive reads, where it first reads from units 1 and 2 and learns the value of X to be 10. It then reads from units 2 and 3 and learns the value of X to be 5. So what is the value of X? From this client's perspective, the read and write operations are non-linearizable. And so to make the solution linearizable, what we need is we either need locking so that each replica allows only one operation to occur at a time, but locking leads to deadlocks, and in distributed systems, detecting and resolving deadlocks requires additional communication, which can again leak sensitive information. And so given that we cannot use locking, we would need another round of communication to order client request. And so that brings me to the replication solution of QuORAM, which is inspired by Lynch and Schwartzman's solution. And so here in QuORAM, every data item has a value V and an associated tag T, which is a monotonically increasing entity. This can be thought of as timestamp-based data stores. And QuORAM achieves its replication, as I just mentioned, in 2 phases. The first is the query phase, and the second is the propagate phase. Looking at the protocol in more detail, here the client that is logically reading or writing the data executes or drives the protocol. And so the client first sends an ORAM read request to all the units in the system and waits to receive the value and the tag from a majority of these system units. For read request, when it receives all these responses, the client picks the value v prime corresponding to the highest tag p prime, or for write request, it updates the tag as well as the value. And for either kinds of requests, the client then sends the ORAM write request to all of the units and waits to receive for an acknowledgement from a majority of these. At this point, the client considers this operation to be complete and successful. So this is how we design a replication protocol that gives us both lock-free mechanism as well as linearizable semantics. Now, having described these two goals, let's go back and look at how does QuORAM achieve access pattern obliviousness. And so for this, QuORAM underlyingly uses an existing ORAM scheme, that is tau ORAM, which is an extension of path ORAM to include concurrent and asynchronous requests. Now, if QuORAM uses tau ORAM as it is without any modifications to it in a naive way, if it integrates it, it ends up fetching the same path twice for every single client request. To see why this is the case, let's recall that QuORAM's replication protocol occurs in two rounds. One is the query phase and then the propagate phase. In the query phase, when the client sends an ORAM read request to the proxy, if you recall from path ORAM, the proxy executes this in two steps. First, it reads, and then it writes the data. Now, when the client sends the corresponding ORAM write request, the proxy again reads and writes the data because it is treating it as an independent ORAM request. So essentially, for every request, the proxies are communicating with the external server 4 times, and 2 of these rounds of communication are completely unnecessary. To mitigate this double fetching, what QuORAM does is it meticulously keeps track of all the ongoing requests in the system. And we do this by introducing a new data structure called incomplete cache map that stores the request ID and path ID mappings for all of the ongoing requests, which is translated as all the requests that have finished the query phase, but have not yet finished the propagate phase. And so to see how this helps us mitigate this 2 rounds of communication, let's go back to the example where a client is sending an ORAM read request to a proxy. And this proxy adds the request and the corresponding path into the incomplete cache map and reads the data. It does not perform any writes here. And in the next step, when the client sends the corresponding ORAM write request, the proxy checks if that entry exists, removes that entry, and then writes the data or the path back to the external server. So essentially, by remembering what requests are ongoing, proxies in QuORAM are able to read the data once and write the data once for every single client request. So hopefully this gave you a high-level idea about how does QuORAM achieve both replication as well as access pattern obliviousness. Now let me spend a quick minute on explaining the performance evaluations of QuORAM. We evaluated QuORAM with 3 baselines. First one is the insecure baseline, but this is fault tolerant. So this is a replication solution, but it doesn't give any privacy or obliviousness guarantees. The second is the no replication solution, where this is a secure system, but it does not tolerate any failures. And third is the OBLAD's idea of relying on the cloud itself to achieve fault tolerance. And for this, we use the open source distributed database, CockroachDB. And we ran our performance on Amazon AWS by placing them 3 replicas on 3 different geographical locations. And we used YCSB benchmarking. Looking at the results, here higher is better, and I'm looking at throughput. On the y-axis, I have throughput, and on the x-axis, I have increasing number of concurrent clients that are bombarding the system with more and more requests. These are the numbers for QuORAM's performance. And in comparison, these are the performance numbers of the insecure baseline. And we see that QuORAM and the insecure baseline have very comparable performance values. And this is non-intuitive. The reason for this is because when we have geo-distributed replicas, the communication across these replicas takes so much more time that we can achieve obliviousness and privacy at basically no cost. And looking at the performance of the no replication solution, where this gives us security, but it is not fault tolerant, we see that this performance is about 2.4 times lower than QuORAM's. And the reason for this is because the solution has a single proxy, which is being bombarded with increasingly higher number of concurrent clients. And also when we have geo-distributed clients, some of the clients are facing extremely long communication latency with the proxy. And this leads to, or this translates into lower throughput values. And finally, looking at CockroachDB's performance, this is about 33 times worse than QuORAM. And the reason for this is this also suffers from the single proxy bottleneck. And another major reason is CockroachDB uses a leader-based replication protocol where the leader is serializing or synchronizing the request for every single client request. And so it has two bottlenecks, which is a single proxy and the leader node that is executing the replication, which is causing it to perform about 33 times worse than QuORAM. We have many other interesting results in the paper. And if you're interested, I would really encourage you to take a look at it. And so this basically concludes this short talk where I presented QuORAM, which gives us both obliviousness by hiding the access pattern and fault tolerance. And we also saw that it gives us significantly better performance compared to some of its baselines. I want to take a quick moment to dedicate this work to the loving memories of Caitlin Scarberry. She was a BSMS student at UC Santa Barbara, and this project started as part of her master's research project. Her input in this project has been incredibly helpful, and we terribly and immensely miss her. I will conclude this talk, and if you have any questions, please reach out to me. Thank you.